There's a level 5 maths module, so it builds on what the other guys who are on a foundation degree done last year in maths and what you would have done in your engineering mathematics on HNC. I mean, there are differences in those maths modules. So what I do to start with is going to pick up on some calculus that we've done last year. But first of all, let's explain what the module is all about. It's got 4 learning outcomes. So first of all, apply further integration techniques and use numerical methods to evaluate functions. So this module majors on calculus. There are a few other things in it, but the mainstay is further calculus. All right. Looking at forming and solving first order ODEs, which stands for ordinary differential equations, and second order ODEs. 3 is evaluate the use of 2D and or 3D software methods to generate models and solutions to engineering components. So that is the content of the assignment largely. And investigate the use of 3D CAD modeling techniques to evaluate models for design performance. So although we're going to be doing some handwritten maths and there is an exam in this module, there's also some stuff that we're going to do with software, so bring software into it. So that's my handwritten answer, confirmed by the software says. Okay, the reason kind of doing that way is you're going to do a hand solution is if you're going to rely on a piece of software to give you a reliable result, you're likely to want to check that result against an answer that you know was correct in the first place. Okay, so that's what comes in. 2 assessments. Number 1, the examination. Okay, that covers learning outcomes 1 and 2. There's a 2 hours duration. There's a little bit of outcome 1 that's outside that, where we're using what's called numerical methods of integration and finding roots by estimation techniques. They're lengthy topics to have in the exam, so I put them in the assignment. Okay. But largely, it's learning outcomes 1 and 2 of the exam, and then your portfolio, which is what effectively an assignment with several tasks in it, is the learning outcomes 3 and 4, and each of those are worth 50% each. Okay. So that's the module. I'm going to give you a handout now and ask you to have a look at this drill. The other thing I'm going to give you is, and the guys that were with me last year probably still got theirs, but one of these, which is the Bible of calculus techniques that we use. Just check that there might be some stuff on this one. I can't remember. No, I think they're all there. We'll find out. You still got yours, Peter?
I do, but I'm not afraid to say it's left the house, I don't pick them up myself.
Oh, first day mistake, eh?
Yeah, I know.
previous work. What do we have to do to that? Is equal to 12 x to the minus 3. And then we carry on that process. Minus 3. Credit for in the exam, but you could also write minus 36 over x to the 4. So bring that indices term back down underneath the denominator. So I'm quite happy for that answer to be the correct answer in an exam question, if that's all you were given to differentiate that term. I very much doubt whether you're going to get one as easy as that, but you know, you never know, I might be generous. What about if we differentiate I? Y is equal to 6. How could I write that with an x to a power term so that I still just had 6 there? Yeah, I can add to that x to the 0. Yeah, and then I apply the rule we've been applying. So bring the index down and multiply. Okay, take 1 off the index, but 0 times 6 is 0 times x to the power of minus 1 is 0. So if we differentiate constants, they then always end up with 0, i.e. differentiate a constant, it disappears. Y is equal to 6x. What's the power of x here? So we can write it as x to the 1. Apply the method. Bring the power down. Multiply by 6, take 1 off the index. X to the 0. So 1 times 6 is 6. X to the 0 is equal to 1. So the answer is 6. So the variable x disappears. So if we differentiate a variable to the power of 1, we just end up with the coefficient in front. What you need to be careful of is if y is equal to x, what's dy by dx there? Yeah. You have to remember that there's an unwritten coefficient of 1 in front of that. So when you apply the rule, that's x to the 1, remember, so you're bringing that down and multiplying it by the 1 and have an x to the o on the end. But I've seen a lot of instances where that mistake is made, where x is on its own and people just deal with it like it's a constant and it disappears. It doesn't, it becomes 1. Okay? All happy with that so far? Yeah? So, if we have a problem like this one, where we're differentiating a number of terms in x, all added or subtracted together, what do? So we got y is equal to 5x to the 4 plus 4x minus 1 over 2x squared plus 1 over the square root of x minus 3. Yeah, you differentiate each term and add or subtract those together. So you do them all separately. So we go, first of all though, how do we rewrite these ones so that we can differentiate? So that one's okay, we can do that one. We can do 4x minus what do you reckon? What do you reckon? That's, yeah, the two, you'd have that. Right? So it's just the x squared that comes on top and the sign changes. Equally, you could write, you don't have to write it that way, you could write it this way. X to the minus 2 over 2. Right? But in terms of wanting to know what the coefficient is, in this instance, I think I'd probably prefer to see it like, yeah. Yeah. Give us 2, then that would be, if that was 2 over x squared, then the x squared would come up and it'd be 2 times x to the minus 2. Yeah? Alright? Well, if you had 2 over 2x squared, what could you immediately do? Cancel the 2 2's out and make that a 1. Yeah? Alright? And then this one, how do we deal with that one? 1 over square root of x. How can we write the square root of x in indices form? X to the power of a half. Yeah, and then we want to bring it to the top, so it must be x to the power of a minus a half. Yep. Minus 3. Now we differentiate each of those terms separately. Right, so have a go at that. First bit is draw down and multiply. Take one off the index, so it's 4 times 5. I'll write this out as we go along. So we'd write that out properly as 20 x to the 3 you should have got for the first bit. Yeah. And then this is x to the 1, so it's 1 times 4. So that's plus 4. Here, as it's worthwhile leaving the sign in between until you see what the index does to it. Minus 2 times minus a half x to the minus 3. Minus 2 times minus a half is 1. Yeah, so it is plus x to the minus 3 in there. You all see where that come from? Yeah, because we got a negative index multiplied by that negative there to change the sign there to positive. This one is minus a half times x to the minus 3 over 2. Effectively add 2 halves to the index, yeah? Which we can write as minus a half x to the minus 3 over 2. And then what happens to the constant? Cheerio. Okay. Again, that would be a wholly adequate answer for an examination question. However, you could write that as that stays the same. That's 4 is plus 4. This is 1 over x to the 3. Minus a half. What 1 over x cubed all square rooted. Alright, but I would give full marks for that in an exam question. Yeah. What, write that as minus 1.5, minus 1.5. Yes. Yeah. But I don't mind you doing that, but I would suggest that you get comfortable with fractions. Okay? Because that's particularly important when you get things like third, 2/3, they're never ending and repeating, and that's you're losing quite a bit of accuracy, particularly with the 0.67 that you round to in 2/3. You're much better to leave it as 2/3. Alright? Yeah? Yeah, if you need to evaluate it, do it at the end. That's like pi, right? In a formula that's got pi in it, never evaluate pi until you have to, right at the end. Yeah? Because quite often, one, they cancel the several pi terms end up cancelling out anyway. 2, as soon as you evaluate that midway through a calculation, you've then got a never-ending decimal that you're going to round and bring in accuracy. So these guys are already well versed in that. Yeah. So if you get a result on your calculator that says 3 pi, just leave it as 3 pi until you've finished your calculation off and just evaluate it at the end if you need to. Alright? Sorry? Oh, that should have a 2 in front. You're right, Nathan? 2 in front of there. Yeah? Alright? So, moving swiftly on, find the differential coefficients of A. Have I missed? Oh, I might. Where I pulled him out of the bird book, he's got a problem 4 in there that I haven't chosen. That's all. Yeah. Y is equal to 3 sine 4x. And the entry in the table we're using is cos A cos somewhat. Yes, sine AX. Sorry. If we differentiate sine AX, we get A cos AX. Yeah. So that's the function. That's the differential. Yeah. We're going to come back to this later, but we can all write the differential as a function with one dash as the first differential. More about that. So what is A in this case? What's the value of A? 4. So we bring that 4 out and multiply. Change that to cos. Keep the 4x. So it is 12 times the cos 4x. I actually like to put brackets around my cosine and sine terms, to be honest. Making it quite clear what you're taking the sine of. As a shorthand, f dash is shorthand for dy by dx in this case. Yeah. If you look at your top of your table, the standard derivatives, the left-hand side's got y or function of x. Yeah. And on the right-hand side it says dy by dx or f dash of x. When you start to talk about third, fourth, fifth, sixth differentials, it's easier to write them in the function notation. Right? So, B, we've got f of t here. So t is equal to 2 cos 3t. The entry in the table here is that cos ax is a function. The differential is minus a sine ax. Yeah. So dt by dx, t is equal to dy by dt, actually y is equal to dy by dt is equal to, bring the 3 out and multiply, minus 2 sine 3t. So 3 times minus 2 is minus 6. Alright? So the sine and cosine functions are fairly easy to do. Alright? If you think about the graph of a sine function, remember sine of 0 is 0, sine of pi is the slope, cosine goes like that. So where the slope of the sine is, cosine is, slope of the sine is 0, slope of the cosine is at its highest. Where the slope of the sine is at its highest, slope of the cosine is. So it tells you that wherever you go in a sine wave, at any point, the slope of that point is equal to the cosine of that sine wave. Graphically. Y is equal to 3e to the 5x. Entry in the table is function is e to the ax. Differential is e to the ax. That's what that exponential function is. You differentiate it, and the differential is equal to that function. You've got a constant multiplier in front. Okay. So in this case, what is a in this function here? You're comparing that with that. So what's the value of a? Yeah, 5. Bring it out and multiply. Times the 3. E. And 5x. 15. E to 5x. Yeah. Right? Yeah. B. Two over e to 3 theta. How do we do that one, do you think? Equals 2 e to the minus 3 theta. Yeah, so we dy by dx is equal to minus 3 times 2 e to the minus 3 theta equals minus 6. Yep. And we can write that as minus 6 over e to the 3 theta as well. Sorry? C, what? Oh, what the next one? Yeah. So C is y is equal to 6 ln x. The entry in the table for ln x is f dash of x is 1 over x. So here it's going to be 6 times 1 over x. Yeah. Which is more normally written as 6 over x. Yeah. All happy? Because that's the basics of differentiation of the types of functions we're going to use. Okay? You certainly aren't going to get any questions as simple as that in your examination at the end of this. The recap of last year, remember. Alright, so what we now want to move on to are the three formulae for differential calculus. That is the product rule, which is where we've got two functions of x multiplied by each other. We have to use the product rule. One function of xu divided by another function of xv. We use the quotient rule. And then if we've got a function of a function, so if we've got one function of x sitting inside another function of x, we use the function of a function or chain rule. Alright, and each of those is a kind of a process, and you kind of need to remember the method for actually using those and keep repeating and practicing that until it becomes second nature, really. Again, these formulae will be in the formula sheet for the examination. Okay, so we'll have a look at some examples. Product rule first. Y is equal to u times v. We use the product rule formula. So here we've got a problem where y is equal to 3x squared times sine 2x. Yeah. And you can see that 3x squared is one function of x, and sine x is a second function of x, and they're multiplied together. We need to use the product rule. So what we do, and I usually split my board in half for this, is let u equal 3x squared. Let v equal sine 2x. Yeah. Then we have to differentiate those two, so we have to find du by dx. So if we differentiate this, what do we get? (6x). Take one off the index. Peter? Yeah. Right. And differentiate v is equal to sine 2x. dv by dx is equal to dv by dx is equal to 2 cos 2x. What we've done there is we've now assembled everything we need for this formula. dy by dx is what we're trying to find. We've said what u is. We've calculated what dv by dx is. We've said what v is. And we've calculated the u by dx. So now we can bring all of those together and say, using the formula, dy by dx is equal to u, and I put these in brackets to start with, 3x squared times dv by dx, 2 cos 2x, plus what we call v, sine 2x, multiplied by what we calculated as du by dx, 6x. And then we can tidy up a little bit. We've got two constants here, 2 and 3. We can make 6. sine 2x. Alright. Can anyone see how we could actually factorise that a bit more? You could if you needed to, you take 6x outside some brackets. Alright? Yes. You can use the dot to multiply. Or leave it out. Put a multiplication symbol in. Problem 12 there says determine the rate of change of voltage given that V is equal to 5t sine 2t volts when t is equal to 0.2. So that looks more complicated. You've got a function multiplied by another function. We want to find, we've got V is equal to 5t, a function c, multiplied by sine 2t, another function of t. Yeah? So what rule are we going to use? Product rule. U equal 5t. V equal sine 2t. Du by dt is equal to 5. dV by dt it's a bit unfortunate we got V twice here, but never mind. 2 cos 2t. Yeah. So now we can put that in the formula. The slope, the rate of change, dV by dt, rate of change of voltage with time is equal to, and then put those in the formula. It starts off with U. So what do we call U? 5t times dV by dt to cos 2t plus V sine 2t multiplied by du by dt 5. Tidy up, two constants, so that's 10t cos 2t plus 5 sine 2t. And then the question is asking you, what's the value of that function when t is equal to 0.2 seconds? So we just say it's equal to 10 times 0.2 cos 2 times 0.2 plus 5 sine 2 times 0.2. Put that in the calculator and see what we get. I think what I've got here. 10 t cos 2t to 5 sine 2t. Have you got your what must we have our calculator in, gentlemen, for calculus with angles, sines and cosines? Must, boys, remember, calculus must have your calculator in radians mode when you're dealing with sine and cosine functions. Doesn't work with degrees. Am I right, Nathan? Is that what? Have you got your calculator in degrees? Yeah. 3.7892 is what I got here. Volts per second. Units required in that. Rate of change of voltage with time. Right? In your handouts, there's a couple of questions on the next page. Well, what I'll do is spend the rest of the lesson having a go at those two. Okay, we'll pick up, because we made a bit of a late start today, we'll pick up on quotient rule and the function of function rule next time. Okay, and then what I do after that is a little bit about some engineering uses of differential calculus, right, which we did do last year, but I just want to remind you of why you might need to use calculus in the first instance, because then we're going to go on to do, and in the exam you will be applying some calculus techniques to real engineering examples and in your assignment. Okay, so have a go at those two examples, please. Looking at them, okay, what's over here is John Bird's answer in the John Bird book. They came out of there. Okay, so that's what you're aiming to get. Remember, that might be a strangely simplified version. So if you can't see where that answer come from, ask me, and I'll try and show you how it simplifies to there. All right.